Okay, so good morning everyone. Welcome to this third lecture of this series. So Dr. Giuseppe Presti has been already introduced earlier. I propose we start immediately. I will have a look at the chat in order to collect questions at the very end.
Very
so
good.
Please.
Yeah. Thank you, Massimo. Hello, everyone. So thanks for coming for this last round of this series, and hopefully we try to put together all we have seen so far and get some a bit more entertaining things towards the end. So what we're going to see today is we're going to use actually this analysis we did, especially yesterday, presented by Isabella, on our model of consonants applied to a number of temperaments or a number of tunings. Now, of course, this is a huge topic. This would require on itself, if you want to look into so many temperaments that have been created over history in different cultures. So we're going to pick a few just to have an idea. And then we are going to look also to the case of what we call the Microtones. So putting more than 12 notes per octave and see what happens. I won't tell much about this grand finale. Okay, I put it more because we are talking about music, so typically you end with a grand finale. But I'm borrowing it from some experimentation in terms of how you can represent, in fact, the space of notes, the tonal space, which is a nice area of research also that we explored for the classes we've given at the university. So let's get started with one of the. So this slide was presented yesterday by my wife, by Isabella, and the story here is, and actually she cannot be here. Like I was not here yesterday because of family constraints, but whatever. So the story here was, for whoever was not present, we recreated the Pythagorean tuning, which is a very classic tuning based on fifths. And we try to see how it matches with our model so that we see where it works and where it does not really work. And the two things that were evident out of the analysis yesterday was that we have first that some intervals that nowadays are considered very important, especially the third, are not really matching the peak of consonants that you can see at the proper ratio, the pure third. They are quite excellent, so they sound bad. And then what we say, the circle of fifths does not close. This is the typical expression in music to say that if you just add up fifths, one after the other, at some point you end up with the last fifth that is very, very short. And then you have the beating effects that we've seen already. So then it's like all of the fifths but one are very well in this place, but the last one is around here, like very down so it really feels dissonant. Again, just as a reminder, this is our best model of consonants, where we pick the best of the compactness way of, so the harmonicity model for the best ratios, and the best roughness model that is actually coming from Plomp-Levelt, then, Helmholtz, Plomp-Levelt, and Atkinson and Kropov, with some variants from ourselves. And there is one parameter that we chose that is on the psychoacoustic side, that is the width of all of those Gaussians is actually a discrimination Limen, with the idea by experimenting that if you are on the peak of the consonants, you have the peak of the perceived perfect consonants. If you get a little bit away from it, but within a discrimination Limen, so within a few hertz, you start to feel the beatings, as we've seen in the first lesson, but the perception of dissonance is not so exaggerated. I mean, it's really like you have a peak which is smoothed around a few hertz on the maximum possible consonants. And then, of course, the more you go away from the perfect tuning, the more the beatings take over, and then it really feels dissonant. This makes a more physical sense compared to the pure compactness model, where by definition you have the peak of consonants on the ratio, that is the good ratio. And then whatever epsilon you go away from it, you go down to 0 because you have a ratio which is, say, for example, I don't know, 3 over 2. Then you go to 3001 over 2000, which is a millihertz of difference, or pretty much, and the expected consonance will be 0. But no, it's actually pretty much the same. So this model is done with a sigma standard deviation of all of those Gaussians, the size of the discrimination Limen. I put it here so to start, and then all of the others will be similar. Okay, so with this premise, we can actually measure a little bit and do even some experiments now what this means. Like, what does it mean in terms that are not at their best? So let's play, no? So we can generate with our tool set a major chord. So the classic one is the C major, so the C major chord. And you already see by the spectrogram that the fifth is perfect, but the third is beating because of the mistuning. Strange that there is a double audio, but okay. You see that it's kind of vibrating, no? So it's kind of okay, but with a little bit of vibration. Same applies when you put a sixth, so the F major. I think there is a loop here. We are hearing the same thing twice, but okay. Hopefully we don't screw up the system here. But so there you get this effect of this is a mistuned third. The fifth is perfect, but the third is a little bit out of tune. Okay, so that was Pythagoras. Now we do a big jump, and then we will kind of go back. But you see, there are many people that discussed about music over the years, and here this is just let's say Western music. Then you can do the same thing on the Middle East music or the Far East music, etc. But okay, for the sake of trying to identify a few interesting cases, now we jump to Renaissance, to this guy called Giuseppe Zarlino from Italy, from Chioggia. So actually Italy. At the time, this was the Republic of Venice. It was not Italy. But okay. So Zarlino was actually one of the first that, okay, Ptolemy already admitted this 5 out of 4 ratio as a consonant ratio, but Zarlino was the first that really kind of formalized it. So there is this kind of paper at the time that he wrote at this time, where he is defining all of the good ratios, which are all the ratios that actually nowadays we know in the Western music. We inherited them. So it's like deciding or stating that all of those ratios are actually not perfect. They are called imperfect because they are a little bit less good than the perfect ones, being octave and fifth, but they are good enough to be used. So kind of promoted for public consumption, if I can say, right? I mean, it's really just a choice in the end of the day. So the choice was, let's use all of those. What happens when we use all of those? Well, then we create a new scale. So we start from the Pythagorean scale, and we fix the numbers that are actually the most horrible ones, with new ratios that actually sound better because they are more in tune. And we use the usual mechanism of jumping by fifth or by fourth, which is an inverted fifth, to generate the missing intervals. So once we do that, of course, we end up with kind of a little bit messed up scale in the sense of it's more complex because now we have well, this we will see in a moment, but we have actually the size of those. So this one and this one, this is in scale. They are different, in fact. So there is what we would call a major tone and also a minor tone, and then the semitone. So what happens here is that it's complicated, but how does it work really? So if we play with this, what happens? We will see that in fact, because we are really choosing the peaks of consonances, so we really choose. I mean, again, it's a choice. We really selected the peaks of consonances. All of the intervals are very pure if we stay on this tonic. We don't change tonic. And in fact, it is observed that a choir, typically, that sings a cappella, they tend to sing this way, because it's the natural way for voices to tune together. So normally a choir would go this way. But then, again, we have this increased complexity because we have two tones. So we have a major tone here, then a minor tone, then semitone, then major tone, minor tone. No, sorry, this is a typo. Minor tone, this is not a major third. This is another major tone, and then a semitone. So it's a kind of more complex scale. And on top, we worsen the situation because the word fifth that we've seen yesterday, so the last fifth is still there. And we also introduce some thirds which are bad, because to be able to get the good third in the right place, we have other thirds that are actually getting bad. But the problem, in a way, was not really a problem at the time, because it was not very common to do what we would do today by what we call modulation or key change. So changing key over the course of the same music. They just stay on the same, so then you tune everything on that one, and then everything is fine. And if you do that, everything is fine indeed. And for example, this is the C major, the purest possible C major that we can hear. Okay, apart the double thing, there is really the minimum possible beatings in this, because all of the partials are overlapping actually quite well, and you can even see it from this detail that some of those partials are higher because it's the sum of the multiple partials. So we have all of the effects working together. We have this missing fundamental we discussed also yesterday, that is stronger because many are matching. There are no beatings, so it all looks good. And by the way, the minor one, the minor one is also quite nice. I don't show you here the plot, but just to hear, I mean, this is a very, very well-known chord as well. And there again, the choice is to use the proper pure minor third. And so this is what was used at the time. But then what happens if I go to something like an F sharp major, so all on the sharp tones, you get beatings on the fifth and on the third. So this is just to be unused or avoided as much as possible. And the problem there is that, okay, a choir can even sing at this level and then they can tune. But if you have a fixed tuning instrument, like a piano, an organ, a clavichord, those instruments you cannot retune all the time. You tune in a way and then that's it. Which means that there will be never the possibility to have a choir that is also singing together with an organ on this kind of tonalities. And indeed, this was not the case. I mean, they were avoiding those tonalities completely. But of course, this is a limitation of this kind of tuning. And actually, this is not even a tuning in a way. I mean, we can't even call it a temperament, because essentially you can just use the scale as it is without doing any modulation at all. So what can we do here? We can fix it in different ways. So I present you a couple of ways, but again, this is an enormous. There are plenty of information around on what has been done in history, what has been done in different countries, etc. But a couple of those are actually interesting to see also what we can do today, in fact. So one family of temperaments that tried to address this problem was this what they call the mean tone temperaments. And mean in the sense of average, we will see in a moment why it's a mean. And so the principle would be just that we want to keep as many major thirds, pure major thirds as possible, but of course we have to tune the fifths in a way that they match. And you see that already there it's like really, so we are kind of stuck to what Pythagoras gave us, fifths, fourths, and now thirds. And now we are trying to adjust on those. Because anyway, those are the peaks in consonance that we see, so it's not like you have so much choice. And then you do your math and you discover that actually 4/5, so this number, corresponds to 2 octaves plus 1 major third plus an extra fraction, which is this fraction, which is called the syntonic comma in music theory, which is exactly what you want to fix, because you really want the 4/5 to match 2 octaves plus 1 major third. So what you can do is that you reduce each of the fifth by a fourth of that, and you get what we call quarter comma, because this is a fourth of that, mean tone temperament. And the mean tone appears here because it just happens that the mean tone, so the tone, this one, is actually the square root, is the average, okay, of course it's the harmonic average, of the major, of the pure third. So it's the square root of 5 out of 4. So you have the third is perfect. This is the mean tone, so square root of third, so that the two tones are identical by construction. So the complexity is reduced. And then the rest gets, okay, of course, the fifth is a little bit out of tune, the fourth as well. The minor third is kind of okay, so looks not too bad at the end of the day. And so what happens, in fact? It happens that the fifths are a little bit beating, but not so much. So this is actually the tuning that has been used, and it is still in use today in the organs. Because actually there you really want to have something that sounds good on a long, so especially with a major third that is pure. Plus, on top, there have been procedures established even in the history when, remember, there were no frequencimeters or like tuning devices. You would just have the diapason. And then how do you tune? By counting the number of beatings. And indeed, you can have a procedure that allows you to tune the full instrument by just counting how many beatings you are expecting between some intervals. And from time to time, you can check that things are right. Typically, you have to check that the thirds are not beating, some of the thirds at least. But then the problem is that the word fifth is still there. Okay, it's a little bit compensated, but it's still there. So the suggestion was don't compose music in what we would call like remote tonalities. For people that know music, this would be like having many alterations, so sharps or flats in the key, but try to stay with not so many of them, so that you don't hit the bad fifths that are still there. Yeah, why not? So, okay, how does it work? Well, again, we can hear how the C major works, and already you can see the waveform. I mean, you see the beatings, but it's not that bad after all. And because they are tolerable, because it's indeed within the discrimination limit of a perfect fifth. And you see the pattern here on the arrow. You see that there is a little bit of beating, but it's not terrible. Again, like the first time, so there is a bit of beating, yes, but it's a kind of tremolo effect. It's not horrible. It was considered tolerable, let's say, compared to. But then let's see what happens if I go to E major. There is more beating because now the fifth is more out of tune and the third is also not very good. So, this is where indeed, again, remember that, okay, this I said in the first, on the first lecture, then okay, people maybe have also changed. All of those sounds are completely synthetic and on purpose without taking into account the resonances of the instrument that very often may hide a little bit those things. So here we really see the sound, the purest possible sound, and we can do the distinctions between the different tuning systems. And you see that the difference is really just a matter of how you align all of those harmonics. If you align well, then it's nice in the sense of no beatings or few beatings. If they are not very well aligned, it's horrible. So that was the conclusion. Do not compose, do not play music on remote tonalities. And I know even people that study organ or organ composition, the typical recommendation is never play some piece of music that was composed, say, in the 19th century on an organ that was built in the 17th century. Because they assume things in the 19th century, typically the equal temperament, that at the time was not applied, so it doesn't really work. You really want to play music of the time with a given instrument. And okay, of course you have to be careful on listening to those kind of beatings, but with organs it's pretty evident because of the sustained sound. So the beatings kind of accumulate; they don't fade away. So it's an issue, in fact. So then, what can we do? Okay, we can have alternatives also there, still staying on those unequal ones. We are going to go to the equal one, of course, in a moment. So one solution was actually, well, one, there are plenty of solutions, but there have been several proposals there, and typically the challenge there was really trying to have a nice mix of pure fifths or tempered fifths, so that you could have some pure major thirds and some tempered major thirds. And a very notable example actually comes from Germany, from Werkmeister, because this is an unequal, what at the time was called well temperament, which is today is also quite well accepted, that Bach, in his composition, the famous well-tempered clavier, so, or Wohltemperiert Klavier, he has actually used this kind of unequal well temperament. And in particular, one thing that apparently is indeed well accepted is that this is like the cover of his book, and Bach himself drew it, right? I mean, this is really by Bach himself, and all of this kind of decoration on top, in principle, is the key, even though Bach never wrote anything about it, so it's just speculations. But again, speculations which are quite well agreed. This is the key on how to tune your instrument. Each of those things is a fifth. When you have the fifth, so the idea there would be, again, I don't know why, from time to time, I have, looks like, see? Mouse, at least I can see. This one, no. Fine. Oops. So the idea there would be that, so we have 12 of those things. So those three are pure fifths. Those are fifths which have to be tuned with 3 beatings per second, and those are fifths to be tuned with 2 beatings per second. So more or less mistuned. And then by doing the full circle, then you can get a temperament that is good to play the well-tempered clavier. Well, nice attempt. Why not? I mean, in the end, and also the time really, the feeling was like each of the tonalities has its own color, its own charm. How can I say? No, because of course they are tuned differently, and if you are enough educated with your ears, you could really feel the difference between playing in the different keys. What today we are actually lost completely because we just use the equal temperament. So the equal temperament, why not? So let's go to the equal temperament. So who invented it? You find anything on the web. They tell you, depending where you look, they tell you that it was invented by the Chinese, by somewhere in Europe. But in fact, the oldest traces I found are actually from Archita and Aristoxenos, that are 2 Greeks from Taranto. So this is actually near Pythagoras, more or less. So they already had the idea at the time that, okay, we got Pythagoras with 12 fifths. So why don't we tune the 12 fifths all the same, so that we just simplify this and we just remove any other problem? Sure. The principle is simple. So we just decide that all of the sharps and flats are enharmonic, as we say. So they coincide. So we choose the middle, basically. But the real problem until recently was that the tuning of this is super hard, because essentially you have the only rational ratio that you keep is the octave. All of the others are irrational, which means that the number of beatings you have to count is not like 1 per second. It's a little bit more than 1 per second for every fifth, for example. And of course it changes, and the only place where you can actually check that your temperament is correct is at the end of the process. You never have a kind of middle check. Like, okay, I got 4 fifths, I should get a nice third. Well, the third itself is out of tune anyway. So the entire temperament is out of tune. It's nice that it works and we are used to it, but it is out of tune. So making it at the time without an instrument was actually difficult. And what we know is that by the 16th century, actually Galilei, the father of Galileo Galilei, Vincenzo Galilei, used it for lutes. So he already managed to get a procedure for that. And then the keyboard instruments, actually this was done very late in the 19th century. So much later, in fact. I mean, this is how history worked. And anyway, there were plenty of discussions like, yeah, but organs, if you do that, then everything is out of tune. We don't like it. So how does it work really? So let's go with this one now. So let's analyze it with our tools. So we have our nice model, and we try and see what happens when we do this equal temperament tuning. And we can say that actually we are pretty lucky because the 50 is actually pretty good. I mean, it's really pretty good in the sense that by chance, I must say, we have that that this equal division of the octave by 12 gets the fifth very well. And probably this is one of the reasons why it has survived also that long, and we still use 12 notes per octave. I mean, that's really the way to match the fifth pretty nicely. Then, okay, the third is actually there. So the equal temperate third is excedent the proper third, the pure third. Same for the sixth, and the minor third is the reverse. It's a little bit shorter than, flatter than it should be. Okay, well, fine. But then, indeed, this is actually when now modulation, so the key changes were allowed for all tonalities. And actually, this diagram is very common in music. It's where you actually put all of the fifths one after the other, and you can use any of them because they all sound the same by definition, by construction. So at this point, you can do whatever you want. So how does it sound with the synthetic sounds? Well, okay, here I play a trick. This one is actually the C major, but using the tune, the timbre that we used also yesterday from a non-sustained instrument, like a plucked string, like an harp. So in this case, it's not that bad in the sense that in the end of the day, you see the beatings, and there is a little bit of beating, but it's there, and it's fading away very quickly. What is beating? Is the third. The fifth is almost not beating. I mean, you cannot even see any minimal beating on that. It's just the third that is beating a little bit. And today we know, but actually this has been known for long, that the tuning of a pianoforte, really, the piano for a concert piano, is done in a very subtle way, in such a way to also mask a little bit this kind of beating, because every key has 3 strings, and the 3 strings are out of tune between themselves. That's why also it's so complex, the timbre of a piano. And by doing the mistuning of them between themselves, you are kind of masking a little bit also the extra mistuning of the thirds, for example. But then what happens if you use the the timbre of an organ, so sustained? This is the sustained one. At that point, the beating is clear, right? I mean, we have this tremolo effect. And the tremolo effect is because of this, that is the third, so the third that is beating. So this is like the fourth harmonic of the third beating with the fifth harmonic of the tonic. Again, the fifth, you see that the beating of the fifth is very, very, so it's one here, one there, so it's very slow. So almost, very difficult to perceive actually. But the third, you can see it. And you can see also from the waveform that it's pretty much messed up, because the period is by definition much longer if you really look into all of the details. So this is where the 12 equal temperament got very common in many instruments, but organs, because organs actually, this is where you want to limit the beatings. So, I mean, this was still felt like, the mean tone temperament is still better actually than this. So, I mean, you have to find a compromise, of course. At this point, we can go further and say, but why do we have to stay on 12? Why don't we go for this kind of keyboards? Apart that it is probably going to be a mess to learn. But this is a keyboard that is featuring what? It's you already have E sharp, which is not F, right? And then you have a double, actually even a triple sharps and flats in between every tone. Why not? So And there again, history has taught us already many things. I mean, today, of course, with electronics, we can do whatever we want. But this, what we would call microtonal tunings, this is actually something that was already experimented long ago. And yes, I mean, the story was always the same, trying to fix the out of tune equal temperament on 12 notes, trying to do something else. So, typical thing is actually, I mean, to give also a bit of context, this has happened in Europe already, but also even nowadays there are many tunings especially like there is an Indian tuning based on 22 notes per octave, which sounds actually quite nice because they still manage to select some nice consonances and also some nice dissonances. Why not? There is Middle East music, I mean, Arab music is well known to use microtones, to use like a quarter of a tone in some places or these kind of things. Then we go back to actually an observation that was made yesterday by Maria Dimou, that is on the historical use of this. At the end of the day, we can measure the consonants in a more or less objective way and give a score, like this is more consonant, this is more dissonant. Now, whether to use the more consonant or the more dissonant intervals, at the end, it's really a cultural choice. So Western music typically tended to use the more consonant ones, but of course you have other possibilities. And typically, Asian music is more going into the dissonant intervals. And there is even notation for that. Maybe some of you have seen this kind of notation where you have a quarter sharp, so well, half sharp basically, so a quarter tone, or a three-quarter of a tone, or like half flat, or a three-quarter flat. Yeah, this is what has been done. Of course, this comes at a cost, because everything becomes more complex at this point. You have this kind of keyboards which are more complex to build. There are guitars which have many more tabs, so you can really play like whatever number of. I mean, of course, then they get also very, very close. For strings, it's very difficult because you really have to find it by yourself, right? So you can play whatever on strings, but you have to be very, very careful in matching the right note for that. I'm not aware of big developments on what we would call the woodwinds. I mean, all of the instruments like oboe or flute, etc., because there it's actually much more complex. Already the half tone is complex, so going for quarter tones or this kind of ratios is really complicated. But of course, today we can do whatever we want. We can take the synthesizer with the timbre we like, and then we play even as whip or whichever frequency we want. So it's true that nowadays there is a little bit of revamp of this kind of microtonal music, and there are groups that are actually composing with these kind of systems using, well, like jazz groups, which are using the typical instruments from jazz. And okay, a little bit of an ensemble of all of those tunings. I would say the first one that is relevant is using 19 notes per octave. And actually, this was even made by Zarlino himself. Like, okay, he realized that the just intonation doesn't really work, so why not adding the missing notes? So we play 19 instead of 12. So the five more are actually, or the 7 more are actually all of the sharps that are not an harmonic with the flats, pretty much. And it actually works nicely in the sense that it's the good way to pick the consonant intervals that were known. Otherwise, a very interesting one is 31. It's like, why 31? Well, again, you really have to try and find what is the best way to pick the peaks, but with an equal temperament, which allows you to do modulations more easily. Remember, the challenge of the just intonation or even the mean tone is that you have tonalities that are unusable. You really have to stay on the near tonalities, like around C or C major. But with this, you can play wherever. So why not? And in fact, 31 tones per octave is quite good at that. And again, this comes from long ago. It's not very modern. And it's very well approximating the major third, the major sixth, and also this thing, which is called the harmonic seventh. And then we have a kind of obvious thing that is, we take the 12 temperament, we just split every note in 2, and we play with 24. This is actually has come much later, even by Euler. But in fact, if you think about it, it doesn't really bring any improvement, because typically the major third in 12 tone equal temperament, you miss it. You're not going to recover it. I mean, you miss it. You have to change with a prime number, not by just doubling, right? So there's no magic there. So it depends what you want to do. I mean, this is also very typical nowadays. And okay, I've seen horrible things with what they call polychromatic tunings with keyboards that are kind of too deep keyboards. So you have about 10 different C with different colors to have all possible sharp levels, which almost goes continuously to the next one. And then you can play, and then you have to play in 2D, but why not? With electronics, you can do, but this is very recent. I mean, this is because with electronics you can tune this very, very easily. Otherwise, it gets complicated. So now let's play a few of those just to have an idea what happens. And typically I take this 31 TET, 31 tones, tone equal temperament, because there are a couple of interesting observations that can be done also on how to use microtones and how not to use them. So this is how a keyboard would look like. Then, of course, you can try and make the 4 sharps between C and D nicely around like in a square. I don't know. You have to invent something, of course, but this is how it would look like. But in terms of tuning, just to study the mathematical properties or physical properties of the tuning itself, you see that indeed the major third is perfect. The fifth, almost perfect, and the fourth as well. And there's also this peak, which is the seventh harmonic, so the harmonic seventh, so-called, which is the 7 out of 4 ratio, which 12-tone temperament doesn't have. I mean, this is a bit like a very flat B on a tonality of C, but very, very flat. I mean, because this is B, and here you see that it's 3/4 of a tone down from the B. Well, okay, why not? We take note of that. We'll use it in a moment. Of course, then you have also plenty of other. I mean, the peaks are already well known. All of the other microtones are falling into just dissonances here, there. I mean, so there are many of those that are pretty much unusable. So the idea there, from what I understand also by studying and looking around what those people do in terms of composition, is to always select a subset. You never play really all of them at the same time, because you get a lot of dissonance, but really a lot of dissonance. So how does it sound? Well, I mean, by the sound, by what you remember, and even by the waveform that you see, it's pretty much like this famous mean-tone temperament. Because, well, yeah, it just works out like that. But with the advantage that this is equal temperament. So you can play the same way whichever chord, which is the advantage of the equal temperaments. And then, okay, just to use a little bit what happens with this seventh that I showed before. The seventh chord, anybody that plays music knows that this is a very standard chord to create tension, no? Because on 12 tone on standard tuning, when you put the seventh, you get beatings, as we now know very well. But this is done on purpose because you are creating tension that has to be resolved. So, okay, this chord is made to be a little bit dissonant, and it's good that it's dissonant. Now, what happens if I play the same chord by using the harmonic seventh? There is much less tension, because it's much more in tune, which means that it's much less like looking for the resolution. So it's not obvious that you use this instead of the other one. Then again, we go back to where to use things. I mean, it's like you have your tools and you decide what to do. The nice thing of this chord is actually this matches pretty nicely the proper harmonic. So it's really like having the 4th, 5th, 6th, and 7th harmonic one after the other. So it's actually relatively stable from this point of view. But, I mean, again, it depends what you're looking for. If you're looking for tension, that doesn't really work very well. And another experiment that you can do is, what about playing a third which is neither major nor minor, what they would call the neutral third? Does it sound good, bad? The ratio is actually close to like 11/9. So already by the ratio, now we know by all of the considerations we've done, is rather dissonant. You also see the plot, look especially here, is full of beatings. And I don't know what you feel about it. To me, it looks really like something out of tune, because it's not a major, not a minor. So it's a measure out of tune. So the usability of this is very questionable. Of course, then again, it's a matter of what you're looking for, etc. But just to say that all of those microtones are really to be used. They are really spicy, let's say. So they are to be used in a very selective way, depending what you want to play. And in fact, if you look around on YouTube, there are indeed plenty of examples. There are groups that even compose using microtones. The typical trend I see is that most of the music is using just the 12 tones that we would normally hear. And from time to time, they put like a little bit of spice here and there, some extra half sharp or a bit more than half sharp, but not really full sharp. This kind of, if you go for this kind of temperaments, it's not really an half sharp. It's a little bit more than that or whatever. So they put these extra notes just to put a little bit of extra spice, and also to stimulate to use those high order harmonics. So the 7th, the 11th, the 13th, which are very common in jazz music. No, the 13th chord is very common, but the 13th chord on 12 tone equal temperament is out of tune. But okay, it's good. I mean, it's used as out of tune, but the 13th harmonic cannot be played because it's actually on C. It would be an F half sharp. Really half sharp. No way to catch it. It's really falling in the middle. So with these kind of tunings, you can actually get that one. Now, whether that one, that is the 13th harmonic, I mean, it's a little bit far. So how much this is important when we do a composition, well, this is, to be honest, this I leave it more to musical theorists, or I mean, it really becomes, again, a matter of personal preference, right? The interesting consideration is from the physical point of view, again, is really how we match the harmonics and how we can play in such a way that we know what we are matching, what we are mismatching. So with that, we have seen a little bit all of those, a few of those temperaments, and we can draw already some conclusions. Typically, the fact that unequal temperaments, even today, are used in organs. Microtonal temperaments allow for many experimentations and some exploratory music, but the additional dissonances are spicy, so you have to be careful how you use them, but why not? And, well, we understand why the 12-tone equal temperament is so successful, because you have it's really a very good compromise. It's still a compromise, so if you really are very, looking for the perfect consonances, it is out of tune. I mean, it's just a matter of physics. It is out of tune. There's no way to get it in tune. But it is actually quite okay even like this. So it has got the success that we know very well today. And, okay, a little bit of work in progress that we are doing with Isabella is actually trying to measure this in a more quantitative way by using our model, where you saw we can measure what is the consonance of the different intervals of a given temperament. So we could define a kind of consonance indicator for the whole temperament. But this is still very much, I mean, this drawing is on purpose like a draft, because it's really a draft at the moment. But just to have an idea of where we could go in these kind of considerations, and why, in the end, even today, there are debates on, the 12th equal temperament is perfect, you can do everything. No, but it's out of tune, etc., etc. Remember that the feeling of out of tune depends on this famous sigma that we chose, that is the discrimination Limen. And it is it is subjective in the sense that eventually you can have people that even by the same discrimination limit that is more or less accepted to be a few hertz around every frequency in the range where we are like the middle octaves, etc. You can have a perception of mild dissonance versus total dissonance, and then this is really more on the typically people that play an instrument and are used to tuning, they are really able to be very, very careful in detecting the perfect consonants and anything outside. So it would be like they have a very, very spiked Gaussian in that point, but other people maybe they tolerate a little bit more. So there is a bit of margin there, of course. Okay, and to conclude with, just 10 minutes, we have, a kind of grand finale in the sense of trying to tell you a little bit on a different area of this kind of science on its own, that is more on the mathematics side. That is, we now take those intervals that by now it's clear that they are the most consonant intervals, at least for the Western music. This is now mostly focusing on the Western music, in fact. Then let's try to memorize for now those three colors, because those three are kind of axes that we'll make to do something like a representation of the phase space of the tones. And what do we have there? In fact, we have representations that were done even by Euler, and this is what the Germans know as the tonnets, that is the network of tones, so tone nets. So it dates from the 1700. So what is the idea? That you try to really draw a diagram where you have, those are two different versions of the same thing, and you see that the important intervals, so the fifths, the sequence of ascending fifths, or the sequence of ascending thirds, are put in a nice diagram, indeed. And by the way, at the time, this diagram was considered aperiodic because the tuning was non-equal temperate. But now we can apply it to the 12 equal temperament, and in this case, it will go. When you do the full loop, then it goes. You have a periodicity in this kind of scheme. So then this was even rediscovered by musicologists and physicists, and the way it looks like today is actually this kind of lattice, where you can recognize all of the notes very nicely organized with those three axes in this way. And focusing on the 12-tone equal temperament now, you see this kind of losanga is actually all of the tones, and then the rest is a periodic repetition of that. And on top, what happens is that the periodicity is both ways, so it goes horizontally and also vertically. So what do we see or what do we learn out of this kind of representations? Well, first, nowadays, again, with electronics and MIDI devices, etc., you can play. I played myself and enjoyed to use this kind of system for example, from this side, there are even others, where you can play your instrument and you see live the notes appearing. And then you see that typically chords built on fifths, you see them. I mean, it's really like a way to visualize the structure of the typical harmony, again, from Western music. I mean, this is mostly focusing on major thirds and minor thirds. So a major chord typically goes like you have C here, E and G. So it's a triangle pointing down, and the minor chord goes up. So like E, A, C, E. And so you have this kind of pattern. Of course, this is because we are really arranging the tones, the notes in this way. But it's interesting what you can then see out of that. And of course, you also have a little bit of effects, like you may have chords that are close graphically, but not really close when you play them together. Or they may become close if you play tricks like modulations, indeed. And there are modulations played around using a pivotal note and then jumping to a different, a very classic one for people that know about music. So this is C major, right? So look at this one. We keep this one and we go there. Now this is, this becomes, what what is that, because this is an F minor, so it's really like changing tonality at this point, because we introduced that, but we can pivot on the note, or you can go in a different direction. This is even worse, because this one is actually a G sharp measure, or an A flat measure. And these kind of modulations are happening. So you kind of represent what you hear. And but I found myself actually as a nice way to visualize what you are hearing. And this is hoping that you don't get this hypnotic view. This is what you get once you take this scheme that, as I say, is periodic in both directions, right? So it's a torus. You can wrap it in a torus. So you have what is it? In blue, you have the circle of fifths, and in red and green, you have the circles of thirds, minor and major thirds. I mean, this is again a way to visualize the symmetry of this kind of temperaments. But all of these, there are even studies on this, even nowadays. Then you can also do other things, like you do a dual representation. So you take every triangle of that and you replace with a single node on a new diagram, which is now having 24 nodes. Each of them represents a chord. And again, this is periodic, with the same way. And in this case, what happens is that the transformations are actually what musical theorists call relative transformation, or parallel or leading tone transformation between chords, which are also very, very common in music. I mean, now we're really going more and more into music, let's say, more than physics or even mathematics. Again, this is something that has been done, and there is even active research even nowadays, in fact. And just to give you a few links, but I'm not going to play those. I will give you one single demonstration. But there are actually people that spend the time to take pieces like this one is actually pretty impressive. This is really, by then, Chopin knew how to use the 12-tone equal temperament. No way to play this on any organ. Why? Because it's modulating all the time. And it's great to see it on this kind of diagram, because you really see how you are moving in this diagram, changing tonality all over all the time. So it's really kind of interesting how you can represent this. And I want to give a mention to this researcher, Moreno Andreatta, that works at the Strasbourg University and is French-Italian. We had actually the pleasure to invite him, well, remotely it's easy, to our lectures in Ferrara. And there is actually a full group that is actually trying to study the extensions of this visualization even in 3D and 4D. So trying to get all of those symmetries. And all of this is called what they call the math music, so the mathematical structures behind music. So again, very much focusing on 12-tone equal temperament, but fine. I mean, this is the choice. I mean, now that we chose that one as the best compromise, let's try and exploit it as much as possible. And to conclude, indeed, I have one demo that I wanted to show you that is actually based on a very, very famous symphony. I'm sure everybody of you heard it. If not, go and look at this recording. It is an excellent recording by this orchestra and Barenboim as the director. And so this is the second movement of the Ninth Symphony. So this is a very, very fast movement. It's presto as speed. And there is a software that was written by this guy that was doing his PhD with Andreatta, and the software is available there. So I just used this software and a MIDI recording of this part for a specific passage, which I wanted to show you, that in musical notation looks like this. For people that know how to read, you can maybe guess what's happening, but let's play it so that you see live what happens on a... Now the double echo will be a little bit of a mess, but okay, let's see. I hope that is not too bad. So this is the tonets at play, where, for example, this one you see, so this part is actually, what is that? This is an A minor, but if you put this on top, then this is a seventh chord, all of it together. And, okay, again, I hope that the audio doesn't get too much messed up. Let's see what happens. Okay, so that was, I wanted just to take this little phrase because it's well known by people that's musicologists, etc. And it's actually Beethoven that very purposely, very deliberately explored the circle of fifths. And you see in the diagram, it's perfect. You really see that it's going straight by changing fifths all the time. And this, to me, is the perfect demonstration that in the end, the 12-tone equal temperament is great because you can do this. You cannot do this with any other temperament. You really need to have all of the fifths well-tempered one after the other to go from C major to, actually this starts in D minor, but it goes pretty much all the way. And then it does a final jump because, of course, he's an artist, so it really doesn't go for all of it, but it goes for a good part of it. And the visualization is actually kind of helpful to really see this kind of transition across the different chords. I would just recommend you to listen to the full recording because it's actually a great recording, this one from Barenboim, so that then you can try and isolate this phrase in the composition. And with that, we are at the end. So a few conclusions on this. I can say that it's kind of a niche field of research. It was a discovery for me and for us when we started to look at it for those classes, and then we learned ourselves apart the contribution that we made. And at least we hope that we have raised a little bit of awareness of how this works, in particular on this, so far, to the best of our knowledge, original contribution about how we perceive consonants in terms of this global model of compactness and roughness. And well, as we said at the beginning, we can only be happy if now you have more questions than what we had when we started. So thanks a lot. And, yeah.
Thank you very much. It was very impressive, I must say. I was not at the previous two lectures, but it was very interesting. Are there any comments or questions on the audience? I will check also.
So thanks again to both of you for three excellent lectures. I'm wondering how much research has been done into, for example, a string quartet, the way they play, because I play the violin to some level. But, you know, we would tend to adjust the third to have, so although to some extent we have to follow well-tempered tuning, then chord by chord, we a bit more like your a cappella choir.
Exactly.
And that can even extend, I think, to an orchestra or to the woodwind section in an orchestra. So how much analysis has actually been done of, like, doing a Fourier transform of a high-quality string quartet or whatever, and actually how they do pitching?
Now, that's a very good question. To be honest, I don't know myself, in the sense of our analysis was more like interviewing people, and actually we know exactly this is actually quite well known, like asking people that play violins. They play different depending whether they are alone or they play with piano or with an orchestra. And this is very clear. And they adjust the tuning depending on with whom they play. But it's an interesting question in the sense of I'm even thinking myself to try and record and then do the Fourier analysis of this. Because to be honest, I don't know myself if there's been any like people studying specifically this kind of because this goes really into the like the instrument part. So how violins play or how woodwinds play or etc. So this I can't really tell. I'm really thinking myself to do it myself at this point because now it's easy to do this kind of. It's just enough to have a proper recording equipment, which is not that complicated, and then do this kind of analysis, look for the harmonics, etc. So I take it more as a challenge, as a way to do this. Also, we have students that play instruments, and we tend to tell them, try by yourself, see that what happens when you play your instrument, etc. Or try to even record your instrument and see the spectrum of, do the full analysis of your instrument. But again, I don't know exactly about existing research on this. Yeah, but we need a microphone now.
You said organs still don't use tempered tuning. So does it mean you can't play all pieces of music in an organ when it's in another tonality? And how does this work when an organ, which doesn't happen so often, but sometimes organs do play together with other instruments, I guess?
They do, indeed. So, well, then it depends. I know for sure there are organs, even like, I had the chance to meet the organist of the church in Meran, Saint-Junien, that is like next door. That organ is new, but it has been tuned with the mean-tone temperament that was very common also in Spain. The guy is Spanish, so was kind of attached to that, and he said, okay, let's tune it like it was used to be tuned. He let me play it, and I can tell you on F sharp is horrible. You cannot play F sharp music, tonality on that organ. But C major is beautiful. And so what do you do there? If you play with voice, it's perfect. Even violins or strings can adapt. They know that they have to adapt. Clavichords are often also tempered non-equal, so when they have to play old music. So I guess it's really a matter of each time, depending on what is the performance, you adapt and you make sure that all of the instruments agree on what they are playing. Otherwise, it's a mess. Then, of course, there are also, I can imagine there are also organs that have been tuned with equal temperament for simplicity, because nowadays it's more common. And then those ones you cannot use if you want to play like long cadences, because you have really too much beating. So you have to adapt. And for sure, you don't want to play an organ and a clavichord with two different temperaments, because otherwise it becomes really unbearable. I'm thinking also, performances even close by. In Geneva, they do Fête de la Musique, and they do this kind of small ensemble. They will have to agree on the temperaments, and they also play old music. So I wouldn't be surprised that they use the unequal temperaments for those ensembles, and they choose precisely what to play in that respect.
I've heard that piano tuners, they stretch actually a little bit the octaves.
They also do that, yes.
Why do they do this, and how does this fit in your scheme? Did you...
Actually, we didn't go that far, but we cheated there, because we said we stretch it to 2 octaves to do the test, because 1 octave is not enough, and we know that the equivalence, the octave equivalence is not really true. You have to stretch at least to 2 octaves. The reality is that we would need to stretch it to the whole thing, because actually it's well known that even the 2-to-1 ratio doesn't really work the same. On the higher octaves, you have to shrink a little bit, otherwise it's part of the nonlinearities of the ear. The perception of the frequency does not go exactly, well, exponential or logarithmic. There is a little bit of distortion there, and then the piano tuners adapt to compensate the distortion. But this goes when you go even above 3 or 4 octaves. Otherwise, you don't feel it. So in our modeling, we didn't consider that. It's just not in the model. But yes, it's an interesting effect that the tuner has to know to tune the full instrument.
Any other questions?
Maybe we check on Zoom if there is any...
On Zoom, there was nothing.
Ah, okay. Then, even like raised hands or something.
Other comments or questions? So then I propose we thank Giuseppe and Isabella, of course.
Thanks also to Isabella that is following us, indeed.
So as usual, the recordings of the lectures will be made available at Indico shortly.
Hopefully shortly, yes. And the slides as well. I will upload them right away.
Thanks a lot.